uniform boundedness theorem, or is also called Banach-Steinhaus theorem. Banach. Look at the spelling. Theorem, or it is also called uniform boundedness theorem. Uniform boundedness. Theorem. Let us write the statement of the theorem. It states that let B be a Banach space, capital B, a Banach space, and N be a non-linear space. Non-linear. Okay. And if Pi is a non-empty set. Non-empty set. C is a non-empty set of continuous linear transformation. Linear transformation. Continuous linear transformation from B to N. From B to N. So all these PIs are functions which are continuous linear transformations from B to N. With the property, what is the special property? We'll see. With the property, what is the property? That Pi of X is a bounded subset of N for all X belonging to B. What we have to prove? We have to prove that norm Pi is a bounded set of numbers. Set of numbers. To prove. So what is given? We'll read the theorem again. So what is B? B is a Banach space. N is a non-linear space. And what are all PIs? PIs are functions from where to where? B to N. They're all continuous linear transformations from B to N with the property that Ti on X, X coming from B. All these are with the property that with the property that this is a bounded subset of N. We have to prove that norm Pi is a bounded set of numbers. Okay, we'll divide this into small steps. The first step is this. Define Fn equal to all the elements in B such that Ti of X is less than or equal to N. Because Ti of X, they have given it is bounded, no? So therefore, Ti of X will be definitely lesser than or equal to some number. So all those free images belonging to B are put into this Fn. And this is for all n belonging to capital N. N is natural number. N is any natural numbers. I'll write N is natural numbers. And where are all these Fn's? All these Fn's are subsets of B for all N. And clearly, our B will be union of all these Fn's. N equal to 1 to infinity. Now, in this step, we are going to prove that CPT to prove that Fn is closed. Fn is closed. So in the first step, we define what is Fn and we prove that Fn is closed. Now to prove Fn is closed, now a set A is closed if and only if it contains all its limit points. Let us take a limit point of Fn. Let T be a limit point of Fn. What is the meaning of a limit point in any set A? This implies there exists a sequence xk anta tagona xk. So where is this xk? Xk is sequence Fn number. So there exists a sequence in Fn such that this sequence xk tends to t. That implies, what is the meaning of sequence tending to t? This implies limit k going to infinity xk is equal to this t. Okay, so this simple. And where are these xk's? All xk's are in Fn. All xk's are in Fn. So if any element belongs to Fn, Pi of that element will be lesser than or equal to n. So since xk, all these xk's, okay, xk's belong to Fn, will imply that Ti of xk will be lesser than or equal to n. Now this happens for all I and also for all k. Very, very important. So for all k it is happening, no? For the limit, the last one, k going to infinity also happens. Xk will also be lesser than or equal to n. Okay, that implies, now I can write Pi outside, then limit k going to infinity. Why I can do this? Bracket for this will also be lesser than or equal to n. This I can do because Ti is dash. All Ti's are there given, they're all continuous. Continuous linear transformation they are given, we use the continuous part, so this limit and Ti can be interchanged. So we get this. And what is the limit k going to infinity? X of k is nothing but t. So Ti of this is nothing but small t. This is not equal to n. So Pi of small t lesser than or equal to n. Therefore, this small t belongs to Fn. So what was t? T is any limit point of Fn, and I got that limit point belonging to Fn, so it contains all its limit points. Therefore, Fn is closed for all n. So all Fn's are closed. This is our step 1. Very, very simple. Now we shall go to step 2. So step 2. Now, what is our B actually? Since our B is union of all these 1 to infinity of Fn. And what is this B? And B is Banach space. B is Banach space. That implies what? B is That is, B is complete nonlinear space, complete nonlinear space, and every nonlinear space is metric space. Every nonlinear space is metric space. So our B is, that is our B is complete metric space. Our B is complete metric space, and B is countable union of all Fn's, and our B is complete metric space by Bayes category theorem. By Bayes category theorem. By Bayes category theorem. Bayes category theorem. Every complete metric space, every complete metric space is of second category. Second category means what? That is, it is not first category. First category. Not first category. What is first category? First category means B can be written as countable union of nowhere dense set. Since it is not first category, very, very important, it is not first category, and B is union, countable union of all these Fn's, and B is not first category. First category. So conclusion. What is the conclusion now? So at least one, there exists at least one set, say Fn naught, such that this Fn naught is not nowhere dense set. Not nowhere dense set. Not nowhere dense set. Not nowhere dense set. No. So what do you mean by dense set? Nowhere dense means what? That implies Fn naught bar is not null. Bar, closure, and interior. Fn naught, closure, interior is not null. And each Fn is closed. We are proved in the first step. So bar is itself. So this implies now bar is itself. So only interior remains is not null. Is not null. Why bar is itself? Because Fn is closed. We are proved in the first step. So we have not null. So this is not null. That means what? This implies there exists at least one element. There exists some element, at least one. We'll call it as X naught belonging to Fn naught. Fn naught. Here also naught should come. Naught is itself. Here also naught should come. So we have belonging to this interior. Okay, and we have a theorem. Any point belonging to A interior, this implies what? There exists an open set U such that X belongs to U contained in U. So using this, see, I have some element belonging to A interior. In the place of A, I have this, and in the place of X, I have X naught. So this implies there exists, I am in metric space, so there exists, instead of open set, I'll have open sphere. So there exists an open sphere. We'll call this open sphere as SR naught of X naught. open sphere centered at x naught, and the radius is r naught. Very, very easy. So now this implies what? How is this open sphere? Open sphere is in between. In the place of u, I'm going to write this. So x naught belongs to this open sphere contained in Fn naught. Contained in Fn naught without interior here. Okay. So, and this implies A is contained in B. So SR naught bar is contained in Fn naught bar. And Fn naught bar is X because it is closed. So we have also any set, I'm taking this set, is contained in its bar, in its closure. Now combining all these two. So we'll start from x naught. So we'll start with x naught, that is x naught belonging to this. So x of r naught, x naught, that is contained in bar of this, that is closure of this set, and that is contained in Fn naught bar, that is contained in this Fn naught. So where is our x naught? X naught, we'll leave this, we'll take the last one, Fn naught. So where is x naught now? X naught belonging to Fn naught. So what is our Fn naught? It contains all the elements of B such that Ti of. So this implies Ti of this element x naught is lesser than or equal to n naught. Equal to n naught, we'll call it as 1. We'll call it as 1. This is our step 2. Now we shall go to step 3. So we are going to use this equation 1. Remember this equation 1, we are going to use that. Now we shall go to step 3. Now what is step 3? Step 3 is this. Step 3. Let us call this S naught is equal to S R naught X naught. S naught. We'll just call it as just rename it S naught. Then by the previous step we have X naught belonging to S naught X naught whole bar. Correct? We have called this as S naught. And this is contained in Fn naught. This is by the previous step only. Okay. Now, what is actually this S naught? S naught is this set. So this is nothing but all the elements, okay, such that the norm x minus center is x naught, no? So x naught is less than n naught. Because of this bar closure is there, so it will be less than or equal to, very, very important, equal to, the radius is r naught. The radius is n naught or r naught. It's nothing but s r naught. We have taken it as r naught. This is r. So this is r naught. Okay. R naught. What is this now? This is it a closed set? It is closed because it is bar. Okay, closed. Sphere centered at x naught, and radius is r naught. Radius is r naught. Now what we will do is we'll just subtract that x naught. This implies next step will shift x naught. we'll just take away x naught now. So this is nothing but the end x minus, this is x here, no? So I'm subtracting x naught, so x naught, such that norm x minus x naught is less than equal to r naught. Now what is this now? This set is it a closed sphere? Yes, closed sphere. Closed sphere. What is the radius? Radius is r naught. Radius is r naught. And what is the center? Very, very important. The center is origin. Because we have moved, we have taken away this x naught. So the center is origin. Center is origin. Now, we'll divide by r naught. Let s be equal to, we'll take this x naught, s naught minus x naught, we'll divide by r naught. What is this equal to now? This is nothing but all the elements dividing by r naught. Okay, all the elements such that norm x dividing by r naught, no, so dividing by r naught here is 1 it becomes. So all, and we're just calling it as x, so x and lesser than or equal to 1. Lesser than or equal to 1. So what is this s now? So this s is it a closed sphere? Yes, it's a closed sphere. Closed sphere and centered at the origin. And what is the radius? And the radius is 1. So therefore, this S is a closed unit sphere. See, radius is 1, no? So I'm writing unit sphere. So S is a closed unit sphere. So this is our step 3. Now we shall go to step 4. So step 4. Now consider norm of Ti of S naught minus X naught. Norm of this. What is the norm of this? This is equal to norm Ti of S naught minus Ti of X naught. Correct? Now we can split this because our all Ti's are linear. So we can split that. And this is, I'm splitting the norm now. So Ti of S naught. Then Ti of X naught. What is the sign here coming? Very, very important. It is plus only. And here it is lesser than or equal to. Right. So using this fourth property, the norm, we get this lesser than or equal to norm of the first one, norm of the second one. We'll call this as 2. Now again consider, take any element. Consider any element belonging to S naught, which is what it is. So I'm taking any element belonging to S naught. And S naught, our S naught is contained in here. Our S naught is contained in Fn naught. So contained in Fn naught. So therefore, we get X belonging to Fn naught. This implies, what is the condition to be in Fn naught? I have Ti of this X will be lesser than or equal to N naught. So this is happening for all elements. x belonging to S naught. So therefore, can I write like this? Ti of S naught is lesser than or equal to N naught. We'll call this as 3. We'll call that as 3. Now, using 1 and 3. So what was our 1? 1 was this. 1 is this. Ti of X naught is less than or equal to N naught. And I have equation 3. So using these two, so using 1 and 3, 2 becomes. So we have, what is LHS of 2? LHS of 2 is this. So I take that. Ti of X naught minus X naught, close the bracket, norm of that will be lesser than or equal to 2 is the first one here. So I'm putting the lesser than or equal to symbol because it's there here. Then what is this? This one is lesser than or equal to N naught. So N naught and plus in 2 I have plus. Then Ti of X naught, this naught is less than or equal to N naught, that is by 1, and we get that is equal to 2N naught. Okay, the next step, we'll divide by R naught on both sides. We'll divide by R naught on both sides. So we have, this implies, we'll rewrite that step. So Ti of X naught minus X naught lesser than or equal to 2N naught. Adding N naught, I get 2N naught. Now dividing by R naught on both sides. Both sides, we get what? We get Ti of X naught minus X naught. Norm of this divided by R naught lesser than or equal to 2N naught R naught. Since R naught is positive, the inequality remains the same. Now R naught is positive, we'll take this inside. So 1 by R naught Ti of X naught minus X naught lesser than or equal to 2N naught by R naught. This is by using the norm property, which is alpha is taken inside. Now we can still take this inside. So Ti of X naught minus X naught divided by R naught. Norm of this is lesser than or equal to 2N naught by R naught. And Ti, this is nothing but yes, we have called it as yes, less than or equal to 2N naught by R naught. That is called this as equation 4. This is our step 4. Now we shall go to step 5. Remember what we have to prove? We have to prove norm Ti are bounded. Okay, the last step to prove that norm Ti is bounded. This is what we have to prove. So we are proving that in the last step using all these things. Now consider norm Ti is equal to supremum norm Ti of X, and that is the definition of the norm X lesser than or equal to 1. Supremum runs over X. That is equal to supremum X norm Ti of X. Norm X lesser than or equal to 1. That means X belongs to S. Belongs to S. And whenever X belongs to S, using 4, we have this is lesser than or equal to 2n naught by r naught by using equation 4. By using this 4, we get this is lesser than or equal to 2n naught by r naught. Therefore, LHS norm Ti is less than or equal to 2n naught by r naught, which is the number. Therefore, all these are bounded is bounded set of numbers. Hence, the theorem. The proof of Banach-Steinhaus theorem is over. Now we shall go to one application of this Banach-Steinhaus theorem. So again, we look at the theorem. So what is the theorem statement? It said that whenever we have all Pi, if this is a non-empty set of continuous linear transformations from a Banach space to a non-linear space with the property that all Pi, the images, Pi of X, okay, is a bounded subset of N, then for all X belonging to B, then norm Ti is bounded set of numbers. So, one application of this, we shall prove one theorem using this Banach-Steinhaus theorem.